Hi, so here we're going to prove lemma 1.3, the so-called collar lemma. And basically this lemma states that with this path of metrics g of t that we constructed previously, we can construct a so-called collar that basically is a sphere times an interval 0, 1. And then we can glue onto that sphere, onto that cylinder, we can glue an outer Schwarzschild region with a specified mass. And so this is going to be very useful in this construction. And so let's go through what the lemma states. It states that there exists an epsilon greater than 0. And now this epsilon really we can take to be any constant, but we're only going to take epsilon to be smaller later anyway, so it doesn't particularly matter. There exists an epsilon and an a naught bigger than 0. This is going to be quite large, depending on g of 0, such that whenever epsilon is greater than this epsilon naught and a is bigger than a naught, then this cylinder, S2 times the interval, endowed with this following metric, satisfies these following properties. Now this metric is 1 plus epsilon t squared times g, so it's a warped product metric, plus a squared u of t, also depending on the point on the sphere, dt squared. And now this u, recall that this is the first eigenfunction of g of t. And this metric satisfies that the scalar curvature is positive, so that corresponds to dominant energy condition. The initial boundary sphere is minimal, and it's also outer minimizing, meaning that there's no other minimal surface in this manifold. I'll denote this manifold as M, this S2 times 0, 1. So the remaining foliating spheres are all strictly mean convex, meaning that the mean curvature is strictly negative relative to the outward normal. So one remark before we begin, I'd like to say that we can arrange for the initial boundary sphere t equals 0 to be totally geodesic. This has some physical interpretation as well. I forget exactly what those interpretations are, but I'm sure I'll mention that later in this presentation. Totally geodesic, how can we do this? Well, we can do this by taking every nth derivative. So in other words, the Taylor series, we're going to take the Taylor series for alpha to be 0, identically 0 at the origin. And so alpha then looks something like this. It's really flat here at the origin, and then it decreases to 0. Recall that alpha was this auxiliary function that we used in the previous lemma when we constructed g of t. So let's begin the proof. First, some notation. We're going to let, this is just going to make calculations easier. We're going to let h of t be this portion of the metric, 1 plus epsilon t squared g of t. We're going to let v of t, depending also on x, be this portion or the square root of that portion. So a u of t, depending on x. And then we're going to let mu of t, depending only on t, to be 1 plus epsilon t squared inverse times lambda 1 of t. So what does this do? What does this new notation do? Now, v of t is an eigenfunction of eigenvalue. The eigenvalue is going to be mu of t. Of course, this is of this bilinear form, and the bilinear form is minus delta. But now depending on h plus Gauss curvature with respect to h of this bilinear form. So v is an eigenfunction of eigenvalue mu of t. And so before I proceed, let me just get some more space. I'm going to save that for later. This is just going to make the computations easier. So first, let's differentiate h. Well, what does this give us? This would give us 2 epsilon t g of t plus 1 plus epsilon t squared g prime of t. And now compute the trace with respect to h of h prime. Well, we get 1 plus epsilon t squared to the minus 1 times the trace with respect to g of h prime, because that's how h is defined right here. And now what does this equal? Well, this equals 2 epsilon t, 1 plus epsilon t squared inverse, trace g of g, which is just 2, plus this term cancels this term, and we're just left with trace g of g prime. And now recall, in the previous lemma, we required, this was condition 4 of the previous lemma, that trace g of g prime is identically 0. And this is where that comes in. So this whole thing equals 4 epsilon t, 1 plus epsilon t squared, inverse. And now, here's a fact. I'm not going to compute this here for you, but if you want to check it, you can. It's a fairly straightforward computation. And that is that the mean curvature of any one of the foliating spheres, so the sphere times t, let's write that, times t, the mean curvature of this sphere is given by, relative to the outward unit normal, is given by minus 1 over 4 v of t, also depending on x, times trace h of h prime. And this is trace h of h prime. And now recall that we chose, remember v is just a constant, times u of t. And we chose these functions u of t to be, well, u of t is the first eigenfunction of g of t. And these are smooth in time. And so u of t and x is a smooth function on this S2 times the interval, 0, 1. So in particular, this is just a bounded term, right? Because this is a compact manifold. So this is all just a bounded positive term. And trace h of h prime, you could see, as t goes to 0, this goes to 0, this stays positive. And away from 0, this is positive, this is positive, this is positive, because we chose u to be smooth and positive on this manifold S2 times 0, 1. And so everything's positive here, and we have a minus sign out front. So in fact, this shows conditions conditions 2 and 3. The initial boundary sphere is minimal, h0, 0. And the remaining foliating spheres have negative mean curvature, t bigger than 0. So in other words, we have proven that the initial boundary sphere is an outermost minimal surface, pardon me. And so that's what it means to be an apparent horizon. So let's continue to prove. We only need to show, number 1, we need to show that the scalar curvature of this manifold with this metric is positive. And so here's another fact. I'm not going to prove this here, but it's just, again, a straightforward computation. The scalar curvature of this metric is given by the following formula. 2 times the Gauss curvature with respect to h minus 2v, oh, this is v inverse Laplace with respect to h of v plus v to the minus 2 all times minus trace of h double prime plus the derivative with respect to t of v over v times trace of h prime. And now what's left is a positive term. This positive term is just going to be, it doesn't really matter because we're bounding from below anyway, but it's minus 1/4 trace h prime squared, and then plus 3/4 absolute value of h prime squared with respect to h. And so this term is bigger than the absolute value of this term. And so we can just ignore this. So we're going to get that this scalar curvature is bigger than or equal to whatever this is. But we can simplify this more, actually. Recall that, in fact, I have it right here, v of t is an eigenfunction of eigenvalue mu. And so if you multiply this through by v, well, you'll see that 2 times k times v minus Laplace v times v, well, that's just going to be 2 mu times v. And so then when you get this v inverse in there, that you get this expression, and then you just get 2 mu. So that's very nice. Of course, mu depends on t. V, we're going to write in the definition for v right away. It's a of t, so that's a to the minus 2. U, depending on t and x, to the minus 2. Trace h double prime. You can compute that for yourself, but I did that ahead of time, so I'll just write in what that equals. We get a minus 4 epsilon 1 plus epsilon t squared inverse minus trace g of g double prime. So that's this term, and then it's just this term. And now recall that v is, of course, a times u, and so you get a constant on the top and the bottom, so that just cancels. So you're left with partial with respect to t of u over u times trace h prime, which we know what that is already. It's up here. 4 epsilon t. Oh, I'm running out of space again. 1 plus epsilon t squared inverse. You can't see that, but that's okay. It's right here, if you forget what that is. Well, let's simplify this a bit. How can we do that? Well, let's recall the definition of mu. We'll just write that in. So that's 2, 1 plus epsilon t squared to the minus 1 times lambda 1, depending on t. And then all this, I suppose we could just keep as is. So let me just write that out again. Sorry, please be patient. Okay, so that's what we're left with here. Now, we can simplify this once more. We actually want to drag, we want to put this all in one term. So how can we do that? Well, let's simplify this a bit. We're going to put this inside the brackets. So we get, let's keep the a to the minus 2, a to the minus 2, u to the minus 2. I'm not going to write the arguments every time, just for clarity. A to the minus 2, oh, and sorry, we also want this term, 1 plus epsilon t squared inverse. I believe, yes. And now we'll have 2a squared lambda 1, obviously, u squared minus 4 epsilon minus 1 plus epsilon t squared trace with respect to g of g prime plus 4 epsilon t, and of course this term came out, and then we're just left with this partial with respect to t of u over u. So let me just move that down so you could still see it. I think you could still see it. Yes, you can. Okay, so just draw a line here so you know where it ends. We want to bound this from below. Well, if we can get this term is positive, remember that u is a positive function on this manifold, And 1 plus epsilon t squared is clearly positive. So if we can control this, then we'd be done. If we can make this, I won't write it all out again because that's a waste of time, but if we can make 2a squared lambda 1 times u squared minus 4 epsilon plus 1 plus epsilon t squared trace g of g prime plus 4 epsilon t dtu over u, if we can control this whole thing, well, then we'd be done. If we can control this whole thing, if we can make this whole thing positive, we'd be done. Now, a few things to note. Well, the infimum over t of lambda 1 of t is positive, because remember that lambda 1 is really linear. Well, it's not necessarily linear, but it's linear in a sense that it would be linear if we didn't have that auxiliary function lambda. Sorry, we'll call it this function lambda. Lambda of t went from 0 to, or it's a function from 0 to 1 to 0 to 1. Starts at 1 and it goes down like this. So if we didn't have this function lambda, it'd be linear, but it's still positive because at t equals 1, lambda 1 is 1. I think I showed that when we proved the first proposition, that when you take the first eigenvalue of a round sphere, you actually get 1. And lambda 1 of 0 is positive, and it's linear in a sense between those two. So this quantity is always positive. Furthermore, infimum of u squared, this is over all t and x. This is positive because this is a positive function over a compact manifold. And then supremum over t of trace g of g double prime, well, is finite because this is just a smooth Riemannian metric. And of course, supremum over t and x of the partial derivative of log u, which of course is just equivalent with partial derivative of u divided by u, just by chain rule, is also finite. So in fact, term by term, we can bound this by something positive from below. 4 epsilon t is just a small number. This is less than 2. Trace g of g prime is finite. And this derivative is also finite. So we can take a large, or a not large, I should say. A not large enough so that, well, scalar curvature is positive. And of course, eventually, since this is bounded from below and these all are bounded from above, we could just take this to be bigger than whatever, minus this constant divided by the infimum of this, and we would have that scalar curvature is in fact positive. And that completes the proof.